This video is a presentation conducted by Jennifer and myself where we show what we created as part of the ZK App Builders program. In this program, we learned how to utilize zero-knowledge proofs in smart contracts on the Mina blockchain. I definitely recommend the ZK App Builders program if you're curious about ZK. Let's look at the presentations. So hi everyone, this is my presentation as part of the ZK Builders program with the Mina Protocol, and my application that I built at the end of this protocol is called Proof of Knowledge. So a lot of times you have to prove that you know something, whether or not you have to prove that you understand investing concepts so you can be an accredited investor, or you may need to prove that you know some knowledge so you can get access to a job or an interview. Now, when you prove your knowledge, there are many different places where that can be stored. You can get a certificate from various bodies, but why not have full ownership of your knowledge in the form of a token and also blockchain transactions which prove that you have answered correctly? Now, the point of this application is to prove your knowledge, and that's why it's called YK Proofs, which is your knowledge proved on chain. So I will be using the Mina blockchain for this. And the reason why the Mina blockchain is used is because we can take advantage of ZK apps. And by creating a ZK app, we can get private inputs. Now, this is really important because since you're proving your knowledge on chain, the transactions that you send normally will contain revealing information such as your answer for a particular quiz. So once one person gets the question correctly, anyone can go back and look at the blockchain history and see the answer to the question. But by using a zero-knowledge proof, we can have private inputs, which is very important for application success because that way you can prove that you know the answer without that information being leaked. We also have on-chain proofs. We can also store large data sets using something called Merkle trees on Mina. And we also benefit from lower transaction fees because a lot of the computation is done offline or off-chain, I should say. And then you just send your proof to the chain, which is the Mina blockchain. So let's go straight to a demo. I already have it loaded on this tab here, so I will just show this. So because we're testing your knowledge, one of the tried and tested ways of testing knowledge is via a quiz. So in this case, we're testing your knowledge about Mina since we just wrapped up the Mina ZK Builders program. So what is Mina? So, these are the 4 questions here. I'll quickly go to the right one, which is a layer 1 blockchain that's based on ZK proofs and has a blockchain of a fixed size of 22 kilobytes. So just going to click submit. This application is running on GitHub Pages and it is connected to the Berkeley testnet. So right now you see this loading sign and it is generating the proof required to send the transaction. So if I go into the console, you probably would see a message printed saying that, which is creating proof. So in the meanwhile, while that proof is being generated, let's go to the command line version of the application because I have implemented both the front end, but I also have a command line version, which is using the local blockchain. On that version, I have more features implemented, so let's go there. So I already have it loaded here. As you can see, the first question is, what is Mina? So if I put the wrong answer to that question, just so you can see that the proof is checking to see if your knowledge is actually correct, let's say I say it's a layer 2 blockchain, it encountered an error, and that is because the value that the proof was expecting is not the actual value or not the correct value. So let me do a retry. And let's go again. What is Mina? So the answer is a layer 1 blockchain that's based on ZK proofs and has a fixed size of 22 kilobytes. The other question, so we have 10 questions to go through here. It would be great if something like this could be interactive, but let's just keep going. So a zero-knowledge proof is a way of proving the validity of a statement without revealing any information apart from the fact that the statement is true. All right, let's go. So what is a consensus model? Proof of stake, we all should know that. What are ZK apps on Mina? So we know for sure ZK apps use zero-knowledge proofs, but which type? It actually uses ZK snarks, so the answer is number 2. What programming language is used to create ZK apps? I think this is a really great feature, the fact that you can use Typescript because it's very much like JavaScript, which is one of the most popular programming languages. So when does a Mina address act as a ZK app account? So it only becomes a ZK app account when it actually contains a verification key for a smart contract. So the answer is 3. What does a ZK app consist of? So you have a UI and a smart contract. How is a smart contract deployed? So if you're familiar with Ethereum, you probably have used something like the Remix IDE to deploy your smart contract. But in the case of Mina, you can deploy a smart contract simply by sending a transaction to the address where the smart contract will be contained that contains the verification key. So the answer is number 4. Is there a limit to the on-chain state on Mina? The answer is yes, and you're limited to 8 fields. And how do you store more data on chain? Well, you can store the root of a Merkle tree, which I imagine many of us would have used for this program because we had a lot of data to store. I definitely had to use that, for example, storing the questions and answers for this quiz. So now it has minted a token because you have successfully completed the quiz. So it says, congratulations, you won. So now it says, do you have an account with us? Let me just see if this transaction is generated. Okay, not yet. So it says, do you have an account with us? I'll just say no for now. Would you like to create one to claim your tokens later? Yes. And it is now going to create that. By the way, this is using the local blockchain. That's why it's so fast. Would you like to claim your rewards now? Yes. So that question and answer, I mean, that username and password is stored in the Merkle tree. Enter your username, enter your password. And now it's going to approve the transaction for claiming the tokens. So for some reason, that one takes a little bit longer. So we'll just wait for that to load. Meanwhile, let's just check up on this one and go to the console. So it's still creating the proof, no problema. Alrighty, and let me go back to the code actually. So let me show you the code that's involved. So just now I showed you how you can run it within your terminal. This is using the local blockchain. So if you go to my code repo, you can see that here. And I can show you, for example, where you would answer the question. Oh, wonderful. So this is a confirmed transaction that is coming from this application, which is where you're confirming the transaction, which is to send your answer for this particular quiz. So I'm just going to click confirm. So that can be sent to the Berkeley blockchain. The transaction has been sent. I do have a link here, which I can't see. Okay, yeah. So you can see that link, it goes to the blockchain, and it probably will take a minute or two to be confirmed. Immediately, once you have sent the transaction, I am now sending you to the other question. And the reason why I did that is because the fact that the transaction is sent shows me that more than likely you have the correct answer. So if it fails for some reason, it might be because of gas fees. So the transaction is not found yet. So let's just give it a while for that to show up on the blockchain. And I won't submit the other transaction just yet. So going back to my code, let's just go to the section where you'd be answering a question. So here you see we're going through the list of questions and it waits for your response. And once it finds your response, it looks for that particular one within the Merkle tree, and then it sends the transactions where you're validating the question response, then signing the transaction, and then doing a proof, and then finally sending it. So this is the code required to validate that you have answered the question correctly. And if we look at that within the actual smart contract, what that looks like, it is right here, validate question response. So it looks at it first gets the root of the Merkle tree, which is stored in the state of the smart contract, and then it takes in the path to your response, and then it checks to see whether or not that is equal to the path that's on the Merkle tree, which is stored in the smart contract. So once that is correct, then the transaction will go through, and that's the behavior we saw within the application when we ran it here, but also the fact that you're confirming a transaction. Similarly for the front end, let me see if I can show you. Yeah, similarly for the front end, this is the form where you see the question responses coming up, and then the method handle submit is called. So in handle submit, you are then calling this, which is called on-send transaction, and you're passing the question response and send. And that, on-send transaction and calls create update transaction. And if you go into the code that actually shows where it's calling the ZK app code, so that's what's happening on this side here. Let's see if this transaction is now showing up. Wonderful. So it went through. So that was the first transaction. So let's try to put the wrong answer for this one, and let's see what happens on the UI version. So it already says incorrect, so there's no need for a transaction to be sent. And let's just put the correct one and send that through. And yeah, so now you've seen the code, you've seen it run in command line, you've seen it run in the UI. Let's just go back to the presentation. So the persons who I expect to use this app are people who are knowledge holders who would like to prove that they know knowledge about something. This can be used in compliance, this can be used in education, it can be used in many fields. Knowledge providers, so you can do many courses right now online with Coursera, even BillSpace, and they might all want to have one way to prove that you know your knowledge. And I think everyone can use this application sort of like a widget and they prove their knowledge and they get a token, and that token is stored on chain. And it can be nice if websites like LinkedIn as well show these tokens. So the features that this app has, you have a quiz, you have token rewards, which I demonstrated in, so that transaction went through successfully. And that's what I demonstrated in the terminal using the local blockchain. I don't have that working yet for the one on Berkeley, which is a test net. And then you can create user accounts so you can claim your rewards later. So the ZK app components used, so I use zero knowledge proofs, of course, and the zero knowledge proofs we use so that the user can send their answer response privately, and that is proved on chain. I deployed on the testnet. I use Merkle trees so that I can store like lots of question and answer data. Recursive proofs I did start, but I didn't actually get to the finish line with that one. But that would be great so that I don't have to send one transaction per question. And I also tested out custom tokens, as you saw. So design challenges. So I would say a design challenge is the fact that you're limited to 8 state variables, but that was easily solved using Merkle trees. Merkle trees were my best friend throughout this program. Also, another challenge was understanding, because I come from the EVM world, understanding the Mina concepts, understanding what should actually be private and how to make sure you maintain that privacy throughout your application was definitely something that I had to take a while to wrap my mind around. But I did get through by, speaking to persons on the team. I definitely did Control F in Discord far too many times when I was searching for issues. And also creating a Mina proof while also keeping the data required for the proof private was something that I had to think about as well. So this is me. I am a content creator. I like to talk about blockchain on social media. And this is where you can find me. And that is my presentation. I really would love to show you the end screen because there is confetti. So let's just see how long this transaction takes to go. Like if you just give it 2 more seconds, we probably could see that confetti. But that is the front end application. You can access it here. You can find my code on GitHub here, and I have instructions showing you how to run it in the README. So you can run from a terminal if you would like to run the local blockchain, or you could also simply just go to the front end, but you're limited to just the quiz app feature. So definitely, if you find this interesting, please reach out to me. I would love to continue working on this. And I have lots of steps here that you can go through to understand why I did what I did. And as well, you can find the smart contract address on the Berkeley testnet here. Come on, load for me. Let's see. So yeah, so this is the smart contract here on the Berkeley testnet. It's deployed to this particular address. So as we saw in the quiz, in order for an address to contain a smart contract, it must have a verification key. So this is the verification key hash. I wonder if I printed that out here on my, did I print it here? Ah, perfect. So as you can see, the hash that I have on my local version, running it on the Mina local blockchain, is the same verification key that I have on the public blockchain because it's the same smart contract that's being used. And then you see we have the ZK app state, and this is where I stored the root of Merkle trees. So 2 Merkle trees were stored here. And 1 Merkle tree is the one that has the question and answers so that we can validate question responses. And the second Merkle tree is where I stored user accounts. So whenever you see that interaction where I had to create a user account, it was actually stored in a Merkle tree. I didn't actually demonstrate that in the front end, but it was deployed to the smart contract because I did have like some usernames like hard-coded, username and passwords hard-coded. So that is why that field is populated. As you can see, I have a list of transactions that I would have been working on from even weeks ago. The ones here that failed, this is where I was testing sending tokens to another address. And as you can see, I have like 2 accounts here. For some reason, those didn't work because of invalid fee access. This error has been the bane of my existence for this program. So definitely I need to figure out how to solve that. But these are the successful transactions from verifying that you submitted the correct transactions. So it seems like I'm not able to show this in time. So I guess still pending. Dun, 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 dun. I guess I would just leave it there for now. I really want you to see the confetti, but actually that's probably motivation for you to go try the application yourself, confirm the transaction, and see the confetti. So thank you so much for watching.
I love it. I think the use case that will be really interesting for is kind of compliance. a lot of times you have to go through like security audits, and like auditors would kind of like want to see whether employees would have done a course or something. And the way they usually do it is like, oh yeah, show me kind of your page where you did the course or something. And like, I don't know, with your app, you could just simply verify the proof that's already on chain. Make everyone's job much easier.
Yes, I love that.
Really like this case is very special. Thanks.
Thank you. So I will stop sharing now.
Sure thing, and I can take over. Let me find the correct screen to share. All right. Yes. So as part of the ZK App Builders program, I created a treasure hunt game, and I called it ZK Schnitzelhunt. The name comes from the fact that in Austria, where I'm from, we call it Schnitzelhunt. So Schnitzel is a famous Austrian dish, and apparently that's our treasure at the end. So let me just kind of like give you an overview how the game works. So the user would start the game, and they're presented a riddle. And then they can share the location. Obviously, if it's not correct, they can retry. But if it's correct, a ZK proof is generated. And then if this is like valid, they would be able to, it unlocks the second riddle. And then you do the same thing again. You share your location. If it's correct, the proof is generated. And it kind of goes on until we generate the final proof. So in my first iteration, I actually kind of implemented this iteratively. So it would, after every riddle, we would generate a proof and submit it on chain. And then in my second iteration, I actually used a kind of experimental feature of SnarkyJS. Namely, you can recursively construct your proofs. And the way it works is, I'll show you also later in the contract, but kind of on a high level, we still kind of generate a proof after the first riddle. But then when we get to the second riddle, we kind of like wrap the second proof around the first proof. And then we kind of like, we can recursively walk through kind of the game state machine. And then only at the end, we submit the wrapped proofs on chain. And it's really useful, especially for, you see this is like a recursive problem. And it's really useful because then we only have like one transaction at the end. So the way I implemented it, I was kind of tied to 3 design decision parameters. We already talked about the first one. A ZK app account can only store 8 fields or 32 bytes. And then secondly, if you're developing a zero-knowledge smart contract, you have to make sure you're using SnarkyJS compatible data types. And that was really important because, location data is usually stored in floating points. So I had to transform the data that the user inputs. And then, another thing that I kind of realized during the game was, or like during developing the game, was that it's very unlikely that the user will kind of share the exact geographical point. So we have to allow a valid range for the riddle. So kind of to solve one of the problems, what I did is I kind of pre-computed this valid bounding box per riddle. And because we already talked about, we can't store all of these on chain. So what I do, I use our favorite trees, the Merkle tree. So I store the hash of each valid location in a Merkle tree off chain. And then I store the Merkle root on chain. And then for every riddle, we have 1 Merkle tree. And then finally, how is the riddle, like how do we know whether a riddle was solved? So given the shared location, we can generate a Merkle proof. I think Alysia already kind of showcased this really well, how it works. And then the smart contract can validate the Merkle proof against the solution root that we stored on chain. So now we can jump into a demo because so my app only runs locally, and proving time, especially on my Mac, is really slow. So what I did is I had this pre-recorded, and I will just show you the recording. All right. This is the wrong thing. Second. Let me swap these things around. Now you should be able to see this recording. Can you see it well? Okay, cool.
Yes, I can.
Thanks. All right, so let's start the recording. So the user clicks start new game and, starts a game. And what happens, because we're running locally, loading SnarkyJS, we're also starting the local Mina blockchain, and then compile the app. And here, the interesting things that's happening, let me actually speed this up a little bit because it's going to take quite a while. So basically, here you see we're building the solution Merkle trees that I talked about. And then I initialize the app. And as I said before, like what we want to do on initializing is actually like setting the Merkle root of each solution tree in a smart contract. And you will see this in a second. Maybe I can hit pause in a bit. So I'm like, after initialization is done, I actually fetch, here it is. I fetch the state of the kind of like of the game before we actually start the game. So here you see basically the solution roots, 1, 2, and 3, and then the current step of the state. And then the user can share the location within the browser. Please ignore the HTML warning. Yeah, and now you can see here, the user shared the location and then clicked submit. And then here, what's happening here is that like the proof kind of gets constructed. So we'll again kind of like speed this up until we, until they actually see the proof. So what I did is, maybe I can just pause here. So what I did is, so we can just see like kind of like what this looked like here. Like once a riddle was solved, we kind of like generate a proof, and I output here kind of this JSON of the proof. So you can see this. Yeah, you can see this here. And then let's continue and go to the next riddle. Now I'm just going to speed this up a little bit. But basically, kind of what we're doing here while we work through the riddles is that we're basically constructing these recursive proofs. Because what you can see is like we're doing the proofs. I'm doing this like really fast so we can watch this at the end. So we're like wrapping the proofs into each other. And then only at the end, so here this like the user now solved the last riddle. You can see this because the current step now is 3. So that's the state that we fetched. And now, we click here this button, we'll go to the next step. And what you see is that now we deploy the contract. And then we can hit the methods that's in the contract, which is finished. And basically what it does now, like, can just speed this up while I talk. So basically what it does, it takes the recursive proofs and then just checks like, is this game in the correct state? So are we in step 3? Has the user solved all the steps? And then it will basically allow you to complete the game if all the proofs are valid. I'll jump into the code in a second, but let me just walk you through how it looks at the end. So now you can probably see. There it is. Okay, cool. So now we also have the confetti. You successfully handled the schnitzel. And what you can see here, we fetch the state again, and then we see like the finish line is true, and that only happens obviously if all the proofs are valid. So to jump into the code, if you go to my GitHub account, it's genpath. I'm genpath everywhere, and then you can find a repository ZK Schnitzeljagd. In the contracts folder, you will find, like this is basically the iterative version that I did in the beginning. And then basically the demo I showed you now is using the recursive contract. I'm not going to walk you through all the code. Please feel free to also read the docs. I tried to document everything as well as possible. So here, is this here? Yeah. Here is the kind of the experimental proof construction that we're using. And you can see here, so what's the most interesting thing? So this is the initialization that we do where we store all the roots as public inputs. And then here, this is the function that we call once we move through the game. And as you can see, it kind of like always like fetches the previous proof and then does the assertion. Like you saw the assertion earlier, it's literally the same, basically checking the Merkle proof against the solution root. So this basically tells us, okay, the location shared is a valid location within the bounding box. And then the interesting kind of like rollout contract looks like this. So it has like one kind of field, which is finished. And then it takes our kind of like recursive proofs. So it verifies our rep proofs. It also checks whether we're in the correct step, because otherwise, if we're in step 1, you can't finish the game. And then finally, it sets the finish to true. So like you saw this in the console log, we finished the game. So that basically means, finish the game and we can submit a proof on chain. So this is actually everything I wanted to show in my app. And yeah, obviously, if you have any like questions, you can find me, Jenpuff, on Twitter. I'm actually hoping to get this deployed on Berkeley at some point. But yeah, let's see what the future brings.
Oh, that's so good. Really nice to see that you got the recursive proofs working as well. So that way, you don't have to submit the proof until the very end. That's nice. And I think this would be very good, useful if you're doing those treasure hunt games like we were talking about before. Like you can prove your location without people actually knowing where the exact location for the treasure hunt is. So therefore, the competition can still carry on. So I think that's very fun.
Yeah.
What was the most enjoyable part for like building this?
Honestly, I think actually like doing the kind of like, first of all, like transforming my problem statement initially into something that like I can actually build a zero knowledge contract with. And then actually diving into this recursive contract. I thought that was like a really interesting feature. And kind of like, improve the performance a little bit of my app.
Yeah, nice. And what was the most challenging?
Honestly, I think actually wrapping my head around zero knowledge in the beginning, I thought that was quite challenging for me. Like I don't really have like a strong math background, but I fell into the rabbit hole, but it's still challenging. I feel like I'm still on the journey to really understanding everything. But it's surely like a super, super interesting space.
Yeah. Yeah, I thought that was one of the most interesting parts. Like, wait, hold up. What zero knowledge proofs? When did this happen? Like, did I miss some classes in school? I don't remember ever learning about this.
It's a bit funny how, like, in the beginning, I was like trying to understand the Where's Waldo examples. And then, suddenly we have like a working zero knowledge app. So I feel like we've made some good progress. Can be proud of ourselves.
Definitely thankful to the ZK team and the Mina team for teaching us this, because I don't think I would have really dedicated my time so much to this if I didn't have that kind of structured support. So that was really good.
Yeah, totally. And totally recommend applying for the Builders program, the 221. There's also loads of other like programs funded by Mina. So that's definitely something to look into. All right. I'm really happy we recorded this. So
Yay.